Hello and welcome back to the Advanced Malware Analysis course. In this part of the course we're looking at initial stages, and in this part of the chapter we're going to be looking at second stage loaders. So this is a follow-on from the last chapter where we looked at malicious Word documents. Now we're going to be looking at the executable or DLL downloaded by those Word documents. So let's just get started. So loaders. So these are payloads dropped or executed on a machine through initial stages, other malware families, or even exploits. So they're used to download the final payload from hard-coded command and control servers or possibly DGA generated command and control servers. So DGA meaning domain generation algorithm. So in this screenshot from the malware traffic analysis website, we have an image of a packet capture file where we can see that an initial malware DLL is being used to download sniff. So that's just one example of loaders when it comes to malware. So they usually contain some form of configuration inside that holds a list of active command and control servers, encryption keys to use for communication, and anything else necessary to download the next phase. We are able to use this to our advantage and write scripts to extract the config and then basically emulate the communications to retrieve the follow-up payload without worrying about infecting a machine and going through a sandbox and all of that. And that's essentially the aim when we go to analyze different malware families. We want to automate it as soon as possible, but we'll get to that part of the chapter after we finish this one. So as you can see on the image on the right, this is actually the ISFB configuration passing function inside of the binary. So it will pass the structure it's got in the binary and use that to locate different values, so embedded executables or potentially RSA keys or encryption keys or whatever it uses to download the next phase. So now we're going to cover a personal method that I used when it comes to analyzing a loader and basically writing emulation scripts and everything for it. So to start off with, we've got to get information on the binary. So we determine if it's packed, we get an overview of possible capabilities and get an idea of possible algorithms inside of it. From there we perform basic static analysis, so we locate the communications routine, locate any configurations if we can find hard-coded values, determine any crypto algorithms, and locate any possible anti-analysis methods. So from there we perform dynamic analysis, and this is done to confirm where the communication routines are, as well as the location of the configs plus crypto algorithms protecting it. And once we know all of this information, we move on to developing a config extractor. So what we do here is we determine the method of parsing the binary to first locate the config. Is it hard-coded? Do we need to use regular expressions? And so on. From there, we extract the configuration and then pass it into an understandable output, so XML, JSON, whatever you want to use. And now we've got a config extractor working and tested on a few samples. We can then develop a communications emulator. So here we use the knowledge of the communications routine and the configuration data to emulate communications and hopefully download the final payload. Or perhaps you're dealing with a sample that only has one main executable, in which case you do this when it comes to figuring out how to retrieve web injects from the C2, additional modules, or anything like that. So while I am developing the config extractor and communications emulator, I'm always performing static analysis and then dynamic analysis. So it's basically constantly looping around. Let's say I'm working on the config extractor, I realize certain bytes are off, then I go back to performing static analysis. If I don't get an answer from that, I'll move on to dynamic and see if that gives me anything useful, and then go back to developing the extractor, re-implement the solution, and then carry on. So now we've gone over my personal method of analyzing loaders as well as explaining what they are. Let's actually analyze our first malware loader. Okay, so the first loader we're going to be covering is an IcedID loader, and IcedID is one of the main sort of samples we're going to be looking at throughout this course. So the full analysis later on will be on the IcedID main bot, and we will also look at the API hooking routine in IcedID in the evasion chapter. So let's go ahead and get started. So obviously I'm assuming immediately it's going to be packed. Let's open it up in PE Studio. We can see entropy is fairly high, not too high though, and we've got a debug path here, which is a good hint that it is actually packed because this is just junk, it doesn't mean anything. There's quite a few imports inside of this binary. If we go to the libraries, it only loads 2 libraries. And the sections, we've got text, rdata, data, resource, and relock. So let's go ahead and open this up in X32 debug and see if we can go ahead and unpack it. So let's view these strings. Okay, we've got quite a few strings here. Looks like compiler strings, so it most definitely is packed at this point. So in that case, we will put a breakpoint on virtual allocate, breakpoint on virtual protect, and a breakpoint on create process internal W. And I also saw it imported IcedDebugger present. So let's put a breakpoint on IcedDebugger present. So now we go ahead and run the sample. Let's open up Process Hacker as well. So we have hit a breakpoint on virtual allocate. So let's hit the return, follow and dump, run the debugger. Okay, this is definitely shellcode. We've got the short jump there and all the shellcode in this area. So we've hit virtual allocate once again, hit the return, follow and dump, and run once more. Okay, we have what seems to be some more data here, quite interesting, possibly an array or something written to the unpacked memory, not too sure at this point. But we have hit virtual allocate again, so hit the return once more, right click, follow and dump, we run again, and here we've got the compressed executable. So if you remember when we were unpacking one of these samples in the unpacking chapter, a similar packer was used for a different sample of malware. I don't believe it was IcedID, I can't remember exactly what it is, but we ended up finding a compressed executable. So we hit the return again, following what we did last time. Now we need to basically search for the decompressed executable in memory. So if we step through this, we move this value into EAX. Let's follow and dump. And this actually looks like the base, I think. Yep, so that's the regular IcedID executable, not what we need. We have this value here, which is again the original IcedID binary. Step over that. And here we have another region of memory, so follow this in the dump. So let's scroll up, see if there's anything here. Nope, that looks like that's in the shellcode. No executable there. So let's keep going on. XORs AL with AL. Copy some data there. Let's follow EDI in the dump. Scroll up. Okay, doesn't seem to be an executable there. So let's keep going on. So here we move EBX plus 7014C2 into ESI. So right click, follow in dump, the value. And here we have the executable. So at this point, I'm guessing this is the decompressed executable. If we scroll up to the very top, we can see the compressed executable. So if you remember when we were unpacking one of the samples from before, they did this same sort of format where they had the compressed executable above the decompressed one. So let's select that, scroll all the way to the end of the memory here. There's no other data, so we want to get as close to the code as possible, just so that we don't end up with a 4 megabyte file. So let's select this now, right click, binary, save to file, and we want to go desktop. File name is dumped IcedID loader.bin. Okay, now if we open that in PEBear, we have all the imports because it wasn't mapped into memory yet. And the only issue we really have here is the raw size of the relock section. I think that's mainly just how we dumped it out. I don't believe that's anything important right now. So we should be able to go ahead and open this up in IDA Pro and see what we can find. So let's go ahead and jump over to our static machine. Okay, so we have the IcedID binary open up in IDA. And as you can see, it's pretty basic for a malware loader. There are a lot more complex ones. So looking at the start function, we have a call to this subroutine, and then it will pretty much go ahead and exit. So let's go ahead and step into this function here. So we'll start off by calling shgetFolderPath and pass in a CSIDL here. And then it looks like it might prepend that file path to something else. So we can go ahead and right click this CSIDL here and go to use standard symbolic constant. And now if we search in CSIDL, we can see that the only symbolic constant here is the CSIDL_local_appdata. So that will get the appdata folder and it will store it inside of EAX here, which points to this PSZ path. As we go down, it will test EAX with EAX, and then it will move the path to the appdata folder into EAX. From there, it will either push the public folder directory or push string 2. So I'm guessing this depends on whether the app data folder exists or not. If it doesn't exist, it will drop it to the public directory. Otherwise, it will push a \. So then it will concatenate the app data folder with whatever has been pushed beforehand. So if this is the app data folder, it will append a \/ to it. Otherwise, EAX will be 0 and it will be filled in with the path to the public folder. So going down, we have a call to string length, get username here, create directory A, and then it has this photo.png path here, which is then going to be concatenated to the created directory. So it looks like it's going to be creating a directory based off of something here. So create directory, path name, pszed path. So it looks like it might be creating a directory based off the current username possibly. So as we go down, it will concatenate photo.png to it. So that looks like the file that's going to contain the follow-up payload. So it'll move this D word into EAX. So if we go to this D word here, we can see it's 1D1105FA. Not sure what that relates to at the moment. Then it'll move this unknown offset into var_24. If we go here, it looks like some more encrypted data possibly. So we have var_24 into ECX. We move 8 into var_20, EAX into var_1C, this 0x248 into var_18, and then EAX into var_14. And then we have a call to this subroutine here. So let's dive into this one, see what we can find. So we have a few instructions here. We do some comparisons, some more comparisons, allocate a heap. Okay, then we have some more instructions here. At the moment, I'm mainly looking for something that stands out, whether that's a configuration parser or whether it's encryption algorithms or something. So let's dive into this one. And immediately I noticed this 0x100 here, which is 256. So I'm guessing there's already some sort of RC4 going on here. So this looks like it's generating the substitution box. It will then scramble it, and then it seems to return. So we can go ahead and name this init scramble RC4. So once it's initialized and scrambled the substitution box, we can keep going down. And I've immediately noticed this XOR here. So what seems to be going on is it will initiate the S box and scramble it, and then it will actually use the S box to RC4 decrypt something. So let's change this to RC4 crypt. And as we go down, it just seems to pop EDI off the stack, XOR EAX, and then increment it. So this is the return 0 branch, and this will return 1. And then that brings an end to this function itself. So this was basically just an RC4 decryption loop, I'm guessing. I don't believe it's going to be encrypting anything, as it's quite near the beginning of the function and the execution of the loader in general. So let's change this to RC4 decrypt, although it might be used to encrypt something later. We'll have to check that out. So we have a few more instructions here. Let's keep going down, see if there's anything else we can find. So this pushes in the LP file name. This could be where it's downloading the data from the command and control server. So let's jump into here. So we call create file A, get the file size, heap allocate, read file, and then close handle. So I'm guessing this function is responsible for checking if there's a photo.png already on disk. And if it is, then it will go ahead and read it into memory and probably execute it like that rather than downloading it from a command and control server. So let's back out of this and change this to check if exists. And if the result of the test is equal to 0, it will take this jump. Otherwise, it will call this here, which could be where it injects it into memory. Let's have a check. So here we see it compares a D word at ESI plus 0x57 with the string IDAT. So IDA shows everything with a different endian. So the endianness in IDA makes the string appear backwards, even though it's meant to be forwards. So if that string exists, it will perform some shift left and shift right instructions here. Move some data around, we allocate a heap, RC4 decrypt something, compare a byte with the value 1, and then it looks like it will just go ahead and return. As we see, there's an RC4 decrypt here. I'm guessing that whatever's stored in photo PNG is RC4 encrypted, and it's also masquerading itself as a PNG file. So let's back out of this and rename this to decrypt PNG file. So let's keep going on. We have this first subroutine call here. We can see there's a call to wsprintf down there. So let's step into this first function. Okay, so we've got some instructions here. Now, a lot of the time when I'm analyzing these loaders and stuff, I don't necessarily look at the individual lines. So I don't go, okay, it's subtracting this, it's performing an AND operation there and everything. Normally I use the pseudocode. So for this function, let's go ahead and jump into the pseudocode just to make it a lot easier and quicker. So we call rdtsc, then we call CPU-ID. So I'm already assuming there's probably some sort of anti-VM or anti-sandbox going on here. So we call rdtsc again, and then we subtract v2 from it. So this could be a tick count or something. So if the first 2 bytes of the D word v8 is not equal to 0, it will go to label 16, which will increment the variable v20. Okay, so if v8 is less than 0xfa, so let's change these to decimals just to make it a bit easier. So if v8 is less than 250, it will increment v24. If it's less than 500, it will increment v23. If it's less than 750, it will increment v22. And then if it's more than or equal to 1000, then it will increment v20. So I'm guessing this is probably used as some kind of anti-VM and anti-debug technique. So if the tick count is less than 250, then it will increment v24, which means it's unlikely to be debugged at this point. So they'll increment v24. And in the back end, I'd assume that they will check to see which value is incremented, whether it's something like v25 or v20. So let's go ahead and name this tick count difference. Okay, now we keep going down. So if it is less than 1000 but more than 750, it will increment v21. And then we get to label 12, which will decrement v1, which in this case is 255. So if the tick count is less than 750, it will actually be 254. So while v1 EAX is equal to 6, it will then call CPU-ID again. Then we do v25 is equal to EAX and 1. EAX is equal to 0x4 followed by 7 zeros. Then we call CPU-ID yet again. And then we call wsprintf and we store data into this string here. So instead of analyzing this function fully inside of IDA, we're going to leave the majority of the analysis for when we debug the sample, so we can figure out how it formats the strings and everything. But for now, we know that it will return a string containing information about the tick count as well as the processor based on the amount of CPU-ID calls. So with the information we know now, we can go ahead and rename this to possible anti-VM. So now we've got the possible anti-VM call out of the way. It will call wsprintf again, passing in this photo.png string here, the value 1, this D word here, which is possibly a encryption key. We saw that earlier, not entirely sure what it is yet. And then v4, which is the return value of the rdtsc call, and v8, which looks to be our string created from the anti-VM call. So let's go ahead and rename this to PC info as it's information about tick count and everything. And then this is going to be return rdtsc. This is an unknown D word, we'll leave that, and then the value 1. So from there, this will be stored inside of v11. So let's rename v11 to URL string because it looks like it's going to be appended, hence the / and the question mark ID equals. So then we have v5 is equal to this offset here. We call wsprintf once more, this time pushing in this offset here, which is also unknown, and it will store it inside of v12. And then we enter a while loop, so it will put URL string into v13. If sub 40164b is equal to 200, then break. So this could potentially be the routine responsible for connecting to the command and control server based off of the value returned. So let's step into this. And yep, it looks like it is. So it uses when HTTP open, when HTTP connect, open request. So it will perform a GET request to the command and control server. It will set some options for the connection, send request, and then it will receive response. It'll then query the headers, query data available, get process heap reallocate, and then it'll read data. So what's interesting here is this HTTP send request doesn't seem to send any data to the actual server itself. So this could possibly be a simple check to see if the command and control server is actually online. So let's rename this to check C2. And we see A2 here is equal to 0, but does it have anything else in it? So we'll push EDI here. What does EDI equal? Okay, EDI is equal to EDX, which doesn't seem to have any other uses. So in that case, it's difficult to say if it's passing the photo.png string. If we jump into here, it'll connect to the second argument. So in this case, we can see there's actually 3 arguments. So this is a problem with IDA sometimes, is it'll only recognize 1 argument when in fact it takes 3. So see if we can get it to recognize the other 2, and it will reanalyze everything. So now we can see that the 3 arguments being passed in, we have A1, which is equal to nothing, V10, which is equal to V16, which is equal to this unknown string here. Not entirely sure what that is yet. So let's rename this to unknown string. Then we have this, let's rename this pointer, unknown string. So then it will push in A2. A2 is equal to 0 again. So A1 and A2 don't have anything stored inside of them, interestingly. V17 gets moved into V11, and that doesn't seem like it's used anywhere. So I'm guessing there's probably another issue with how IDA has displayed things here, as I would expect V12 and V11 to be used, but they don't seem to be used. So F5 again. Okay, still doesn't return anything different. So it could just be the way IDA is displaying things, but we have a basic idea that this string is going to be appended to the URL, and then it's going to perform a GET request. It doesn't send any data to it because the data is appended to the URL, and so there's no other data that we're missing here. And so in that case, we can just continue analyzing on from here. We'll cover all the details when it comes to debugging it. So it will check the command and control server, and if it returns 200, it will break from the loop. Otherwise, it seems to loop back around. So v5 is incremented, and then v5 is equal to this unknown value here. And then A1 and A2 is equal to 0. And then it will store v5 plus 1 into unknown string. So based on the fact that it will loop around and constantly change the value in unknown string, my guess is the unknown string could potentially be the command and control server address. So if we step into check C2, check for argument 2, we can see that it is using it for connecting. So with that knowledge, we can change this to command and control URL. So the command and control URL seems to originate from this offset here, although all other mentions of it seem to point to the 1 byte before it. So if we select this and press X to find cross-references, we can see that it has a few cross-references. So if we go to the first one, it's inside of this communications routine. So let's just rename this to comms and then click OK. So if we find cross-references again, we can see that only one of the cross-references occur outside of the communications function. So let's view that. So it moves it into V10. It will then move the data inside of v10 to v10, v12. So it looks like it's just copying it to the value v10. So scrolling down, we move that into v13. Okay, doesn't seem to be any encryption or anything going on here. So it looks like it's just copying it to allocated memory. So let's find cross references to this here. So it's in this subroutine back here. Okay, that's interesting. It seems to occur just below the actual comms routine, and there doesn't seem to be any decryption going on. So potentially what's happening is it will copy the command and control information. So the configuration inside of the loader, it will copy it to the received binary, to the received main module. So obviously it's too early to say right now what's going on, but let's go back into comms. So it will break and then return 1 if the command and control server connects. So let's back out of this. So it will return 1 and then either checks to see if it was able to communicate or able to decrypt a file. And if it wasn't, it will return 0 from the looks of it. Otherwise, it will call this subroutine where it creates a file. It will write the file based on the LP buffer. So LP buffer here is argument 1 for the comms routine, which is most likely going to be the retrieved PNG file. So it's going to write it to PSZ path, which is equal to that photo.png thing we saw earlier. So it will write that to the file, and then it will return from this if statement and call this subroutine here. So let's go ahead and rename this to write PNG. So once it's written the PNG to the photo.png file, it will call this subroutine here, which will allocate a region of memory, move that into v5, seemingly copy some things over to that region that was allocated, move some more things over, so a few D words, possibly the configuration. We can see mentions to that URL offset we saw earlier. So this is all copied over, and then virtual protect is called. So then we'll return result, which is equal to v5, so the allocated region of memory. So v2 here is equal to the allocated memory. If memory wasn't allocated and v2 is null, then it will return 0. Otherwise, it will return v2 plus a pointer to v2 plus 8 and then pass in the argument v2. So that looks like it's possibly executing the main module. If we back out of this function here, so let's just jump to xref, back to the start, it will go ahead and exit process. So I'm guessing here is probably where the main module is executed. And this RC4 decrypt function, I'm guessing it is responsible for decrypting the configuration, as we have a check if the file exists, a decrypt PNG file, a comms function, a write PNG file, and then a allocate region of memory. There's no other functions that could be responsible for configuration decryption. So I'm guessing the configuration is stored at this offset here, or at the very least the key is stored here, and then we have the configuration stored here. So after performing some basic static analysis and naming all of the functions inside of the loader, what we can go ahead and do now is jump over to the dynamic analysis machine and perform some dynamic analysis on this IcedID loader itself and see if we can determine exactly how the configuration is stored, as well as if it's possible to automate extraction of the configuration and decrypt it, plus analyze the communications routine in depth. So let's go ahead and jump over to the dynamic VM. Okay, so we have the IcedID sample open in a debugger, and we are at the entry point right now. So there's the call to the main function and then the exit process function. So let's just view the strings quickly. We're interested in the configuration extraction as well as the method of communication. So to start off with, let's step into this function here. So it will call get folder path, but it's unable to locate it apparently. So it should then append the public directory to it. So if we take the jump, it will push this value here, follow that and dump. Okay, so it pushes the backslash, so it did locate the app data folder. So stepping over this, we concatenate the strings. So if we follow this dword and dump, you see that it appends the backslash there. So if we keep going down, we have the string length. Okay, now we have the call to get username A. So then it will create a directory in the app data folder called din admin. and this is where it's going to store the photo.png in. So it will then concatenate the photo.png onto the file path name. So here we see it's added photo.png. Now we step through, and now we're at the RC4 decryption routine. So we can go ahead and label that for us. So we could migrate the IcedID database over to it, but in this case, we're just going to be doing quite a quick analysis. So let's label the address here. So this is going to be RC4 crypt. So there are a few values for this function. It doesn't necessarily get pushed, although it does get moved into EBP minus 14, 18, and so on. So let's follow the first argument in the dump. Okay, it's nothing important. Second argument points to the base address. So it's not really a stack-based thing. We need to look at the EBP minus 14. So let's follow the first value in the dump. This points to an offset inside of the program. I'm pretty sure this is the R data section or something. So that's the first argument. The second one is 0x248. Then the third argument in this case is, I believe, the same offset. Let's follow that. Yep, it's the same offset as the first argument. The fourth argument has the value 8, and then the fifth argument seems to be a pointer to this offset, which is 8 bytes at the start. So before we've even started analyzing the function, I'm going to make a guess that the first 8 bytes here are actually the RC4 encryption key, and then the rest of the data is RC4 encrypted with that key there. So the main reason I think this is because the first and third argument are offsets pointing to this byte here, and so on. There's no reason it should start like that. It would normally start at E3 if there was another key somewhere else. So I'm going to assume that this is the key they're using for decryption here, and then the rest of the data here, let's select all of it, interestingly is 0x248 bytes. So it pretty much matches, it makes sense. So as soon as we step over this, we should see it being decrypted unless they go ahead and call virtual allocate. So let's actually step into that just in case they do. And it does look like they call RTL allocate heap. So let's put a breakpoint here and hit the return. Okay, so it never called RTL allocate heap. So it decrypted the configuration where it is. It didn't allocate new memory for it. So the configuration starts at this offset here. We have an interesting D word here, not sure what that is. Then we have the value 2. Then we have /index.php, followed by quite a few null bytes. And then we have the command and control server URLs. So we have this first URL here, the second one here, third one here, and the final one there. And if we scroll down, is there anything else added? Doesn't look like it. So this is the huge config of the IcedID loader. So now we know how it's stored. We can go about extracting that later on in the next part of the course. But let's go ahead and return out of this function. So now we know where the URLs are stored. What we want to do is we want to analyze the communications routine. So let's step into this one. This is just checking to see if the photo.png file already exists. So let's hit the return, step out of that, and we go into the comms routine. Now we're in the comms routine. This is going to be the anti-VM detection thing. So let's just label that so we don't get confused. So anti-VM stuff. So it is potentially anti-VM stuff in the sense that it gets information that could be linked to a VM, and that information is sent off to the command and control server, and then the C2 can decide if it wants to respond or not. So let's check what arguments are pushed to this. So the first argument is this value here, possibly allocate to memory or something. Let's see, can't follow that, nope. Second argument looks to be the pointer to the base address. Yep, the base address of the executable. Next argument is an offset in memory, follow D word and current dump. Okay, looks like another one. Okay, and it just keeps going, so nothing really important there. So let's go ahead and step into the function. So we have a few move instructions here. Then we call rdtsc. So according to Wikipedia, let me just read you the definition. So the timestamp counter is a 64-bit register present on all x86 processors. It counts the number of cycles since reset and the instruction rdtsc returns the timestamp counter in edx::eax. So the higher value is stored in edx and the lower is stored in eax. So we'll see once we've stepped over this function here that eax here and edx are going to be changed. So we step over that. So this gives us the time since the last reset as a timestamp counter. So if you remember when we were looking at it statically, we saw it called it twice and then compared the difference. So let's go ahead and just note this so we can see how it works. So we've got 4 zeros, 1 DA6, and then 8117B35. So that's the first result from the rdtsc call. So now we continue on. We call CPU-ID and check in these values here. So now it moves EBX into EAX plus 4, follow EAX plus 4 and dump. Then it will move ECX and then it will move EDX. So this is the data retrieved from the CPU-ID instruction. And now it will call rdtsc once again. Step over that. You can see there's a huge difference in the values. So now we have 1E0A and D1AC99ED. So it'll subtract EAX from ESI, and ESI contains the previous value. So in this case, EAX is equal to 50951EB8. It will then subtract EDX from ESP plus 1C. So EDX will now be 64, and it will then test EDX with EDX, so it's 64. And we hit the first increment as that is less than 250. So it will increment this ESP plus 16. Step over that. It will take us back up to this rdtsc thing, interestingly. So we didn't see this one before. So we run the same instructions again, this time. Then we move some values into EAX plus 4 again. So we'll move these values into EAX plus C. It calls it once again. We go through the same loop, increment this value again, follow and dump. So now it's value 2. So we loop through this 256 times, interestingly. So what we can do is let's put a breakpoint on here and run. So the value here is now 256. So let's continue on. Interestingly, it would be a pretty bad anti-VM technique, I'd guess, because even if you step through it once, you wouldn't step through it again, and you also wouldn't take quite a long time to step through it. So I'd be quite confused if it was actually an anti-VM technique, but anyway, let's keep going on. So we call CPU-ID again, and now we move EBX into ESI plus 4. So let's follow ESI plus 4 in the dump. So we clear that out, XOR ECX with itself, move EDX into ESI plus C. So we're just sort of zeroing this all out, it seems. Then we move ESP plus 28 into AL, and AL, move AL into ESP plus 1B, move 4 and then 7 zeros into EAX. So this is where it gets the hypervisor, I believe. We should see VBox somewhere, so VirtualBox. I believe if they pass in a 4, that means they're trying to get the processor information. So if we step over that, and then follow ESI plus 4 in the dump. And here we go, we see VBox being passed in as a string, so they definitely do try and get the processor information. Okay, so it's VBox, and then we move it again, so it's just a string containing VBox. So if we were going to try and evade this, we would go ahead and select this string here, and then we go to binary, edit, and we change the string to another valid string. So you could change the string to something like AMD is better. I believe that's AMD's processor string, but there's a long list of them. I will leave a link as well if you want to go check those out. So anyway, let's continue on. So now we're on the wsprintf A call. So if we continue on, we can see all the values pushed. So if we follow this do and dump, this will contain the result of the wsprintf call. So if we step over this, we can see that we've got a bunch of zeros here. We've got FF for the incrementation that we saw earlier. We have this 4 and then 6 zeros and 36. So that is not the VBox string we saw earlier, although I believe that 6 at the end corresponds to VBox. So once it has created the string, it will return back to the communications routine where we have another call to wsprintf. So we push the string that was generated in the anti-VM stuff. Then it retrieves the timestamp again. So we step over that. Then we push the lower D word of the timestamp to the stack. Then we push this D word here. Let's follow that and dump. Okay, that seems to be possibly a cookie or something inside of the config. So we have the 8-byte key here. And then we have this D word here that I wasn't too sure about. So that could potentially be a campaign identifier or a botnet ID or something like that. So we'll push that to the stack. Then we have ESP plus 4C moved into EAX, which is this value here. So not too sure what that is at the moment, but it does push it. So let's see what happens. It'll push the photo.png string. So EAX is actually the location. So this bit isn't anything useful. It's just where the photo.png string will be stored. So we step over that and call wsprintf. So now it has created the photo.png string. So we have ID is equal to the campaign identifier, the first D word here. So it's stored as hexadecimal. Then we have this D word here, which is the timestamp that was retrieved up here. And then we have the results of that anti-VM function and the processor value. So in this case, it's VBox. So that's the basic string that's appended to the URL. So let's keep going. We call wsprintf again, but this time we push in the URL this time. So what's going to happen is it will append the photo PNG string to the URL. So step over that. We've got the URL there. And okay, it actually just seems to have converted it to a wide format. So let's keep going down. We call wsprintf again. This time it seems to be converting the photo.png string to a wide as well. So if we follow this and dump and step over that, okay, yep, so it's converting it to a wide format, probably going to be calling win HTTP send request W. So now if we step through this, it'll move the port into EAX, and then we step over, step into the function here, and we've got to the communications function where it calls win HTTP open and everything. So the command and control servers are down at this point, I believe, but we can still briefly step through this and see how it works. So it'll call win HTTP open. Then we have a call to connect where it passes in the URL here, and I don't believe it will connect, or it might do. Okay, so it'll open the request to the previously connected URL. So it'll do a get request, and once it's done that, it will set an option here, and then we go about sending the request to the command and control server. As it's down, it most likely will fail, and so it will end up looping back around to the different URLs. So as you can see, it sent a packet, but it won't get a response because I believe this sample is probably a week or two old, and so it's not going to get a response. But that pretty much sums up the communications routine and the configuration extraction. So the dynamic analysis has pretty much come to an end. We can step back out of this and see how it loops back around. So we'll jump back around, we'll compare the values to 0, and then the program will sleep for quite a long time. But yeah, that pretty much brings an end to the dynamic analysis stage of this. So we've done static and we've done dynamic now. We have a good understanding of how the config is stored. It's RC4 encrypted. In the data section or the RData section, we know where the key is located, the first 8 bytes of the RData section or data section. We need to double check, obviously. And we also know how the communications work. So the packet is made up of information about the processor. It's got a timestamp in it. It has the first 4 bytes of the configuration stored in it, as well as a few other things, plus the /photo.png. So now we have all that information. What we can go ahead and do is in the next part, we're actually going to go and write our own extractor for this loader, as well as our own emulator for it. So we're able to extract information from any new IcedID samples and then go ahead and emulate it. Obviously, the emulator won't work because the command and control servers are down. But what we're going to do is we're going to basically compare the output of the debugger with our emulator. And so if the packets match, we know that our emulator is working just fine. So yeah, that brings the analysis of the IcedID loader pretty much to an end. So I have another loader lined up for us that we can statically analyze, dynamically analyze, and then automate the extraction of the configuration and then emulate later on. So let's go ahead and get over to that now.